All right, welcome back to chemistry. And so what I'm going to talk about this time is I'm going to remind you a little bit about what a solution is and some details that you have not learned before about it. And then I'm going to spend a lot of time talking about how we determine the concentration of a solution. This is very important to learn, especially if you're going to take a job in a lab somewhere. So let's get right to it. Let me give you an example of a solution. Let's say you have table salt, okay? And let's say you don't have a ton of table salt. You just have a little bit of table salt. And let's say you dissolve that in the water. And let's say you dissolve it so well that all the salt is completely dissolved in the water and has not settled down to the bottom of, say, the beaker you have. So that would be a homogeneous mixture. Whenever you have a homogeneous mixture of any kind, and you know from the past discussion there can be many varieties of that, whenever you have a homogeneous mixture, it is a solution. Now there's some details about this that you need to know. So usually you are dissolving one kind of pure substance into another kind of pure substance. And so the pure substance that you don't have a lot of, it would be the salt in this example, would be called a solute. Now the other pure substance that you have a lot of, that you're dissolving the solute in, is called the solvent. So the thing to keep in mind is that a solution is comprised of a solute, which you don't have so much of, and a solvent, which you have a lot more of, and that makes a solution. Now, there are many different kinds of solutions, as I kind of talked about before, and it depends on what phase you are dissolving into another phase. And so a fun, kind of interesting example of a solution is air. Because air, what you have is you have a bunch of pure substances mixed together. So as you probably know, air is comprised of mostly nitrogen gas with some oxygen gas and a little bit of argon gas, and then there are other components in air as well. Now, these are pure substances mixed together thoroughly. So this is a homogeneous mixture, and so this would be a solution. Because oxygen is a lesser percent than the nitrogen, the oxygen and the argon, for example, because there's much less of that, those two can be considered the solutes, while the nitrogen would be considered the solvent. Now, there are plenty examples of liquid solutions. So you can dissolve a gas in a liquid. For example, carbonated beverages, you are dissolving carbon dioxide into the water. And so when that happens, the carbon dioxide, there's probably less of that than the water, so the carbon dioxide is a solute, the water is the solvent. So that would be a homogeneous mixture in a solution. It could be a liquid mixed with a liquid, and there's an example there, or a solid mixed in a liquid, as I just mentioned before. Also, interestingly, there are solid solutions. You can have a liquid mixed in with a solid. In that case, what dentists use is a compound, or rather, I should mistake there. What dentists use is something called a solution, which is a homogeneous mixture again, called amalgam. And there the liquid is mercury mixed in with the solid, which is silver. And then also there are solutions of solids dissolved in solids, and so we talked a little bit about that before. A good example of that is a penny, where in the pennies before 1982, they are made of a little bit of zinc element mixed in with copper element. And it's so thoroughly mixed in is that the penny will have properties sort of in between zinc and copper, more toward copper because there's more of it. But whatever those properties are will be the same wherever you would sample the penny. Okay, so one thing you have to learn, which is very important, is you have to learn how we measure the concentration of the solute in the solution. And that is through something called molarity. And so molarity is pretty easy to calculate for the most part. It is merely the moles of solute divided by the liters of solution. Now, it's important, when you use this formula, you have to make sure that the solute is in moles and then the solution volume is in liters. For example, you could not have moles and then divide it by milliliters. That would give you a wrong number. If you have moles, you must divide it by a volume in liters. And when you take those two numbers, you get the molarity of the solution. And so the symbol for molarity is the capital M. Okay, so let me give you an idea of how you would produce a 1 molar sodium chloride solution in water. What you would do is this. You see in that picture we have a flask there with a long neck. That is called a volumetric flask, and it allows precise determinations of volumes of liquids. And so if you wanted to make a 1 molar solution of sodium chloride in water, what you would do is you would dump in the grams amount of sodium chloride needed for that 1 mole into the volumetric flask. And the grams amount would be 58.44 grams. And so you pour in that mass, or 1 mole of sodium chloride, into the volumetric flask. Then what you do is you add water to the volumetric flask to the line on the neck. Once you get the water there and the meniscus is at the bottom of that line, then you have exactly 1 liter of water. So what you have done is you've dissolved 1 mole salt, which is 58.44 grams, into 1 liter of water. And so you have a 1 molar solution. Okay, so now what we should be able to do is take that simple equation and then try to solve some problems with it. And so some problems are usually pretty simple, but then they get a little bit more complicated, as I'll show you. So let's do the first problem, which is pretty simple. But let me sort of give you some guides on how to solve these problems. So the first problem is this. What is the molarity of a solution with 8 moles of solute dissolved in 10 liters of water? So usually what I do is I set it up like this. I write out variables. Let me get a better pen. There we go. So there is molarity, which is symbolized by M. And then another variable I'm going to write out is moles, solute. So I'll write SOL apostrophe T for moles of solute. And then you have liters of solution. Okay. So we've got those variables written, and so now all we have to do is assign variables and see if we can solve it. Okay, so we're trying to find molarity, so I'm going to put a question mark there. We have 8 moles of solute, so I'm putting an 8 there, and we have 10 liters of solution. So we note that molarity, which is symbolized by the capital M, is equal to the moles of solute. I'm not going to write out solute here, over the liters of solution. I'm not going to write out solution here. And so the question is this. Can we solve for M? Yes, because moles of solute has been assigned a number and the liter solution has been assigned a number. So it's just plugging in 8 divided by 10. And so the molarity of this solution should be 0.8 molar. So you can write out molar if you want. That will be the units we're going to use of concentration. Or you can write 0.8 capital M. That's another way to write it. But there's a third way which I want you to get used to. Remember, molarity here, the molar concentration, all it is moles per liter. So you can also write correctly 0.8 moles per liter. And that would be perfectly fine. So let's move on to the next one. Okay, next one's a little bit trickier. So what is the molarity of 60 grams of sodium chloride in 120 milliliters of water? So again, I'm going to assign variables and see where we're at. Okay, so we're trying to find molarity, so I got a question mark there. So we have 60 grams of sodium chloride. So the sodium chloride is a solute. Now we have it in grams, but again, to use the molarity formula, we have to convert that to moles. So that's a conversion we're going to have to make before we throw that into the molarity formula. So we have 60.00 grams, and let's get this into moles right now. So we would divide it by the molar mass of sodium chloride, and I just kind of know at this point that the molar mass of sodium chloride is 58.44 grams. Okay, I'll do that math in a second. Liter solution. Okay, again, the problem is we don't have a value in liters, but we do have a volume, or value a volume in milliliters. So 120 120 milliliters. And so we have to get this into liters. So we have to convert milliliters to liters. And so I remember that 1 milliliter is equal to 1 times 10 to the negative 3 liters. So times 1 times 10 to the negative 3 liters over 1 milliliter. Okay, so we can do some math really quick. So I'm going to take 60 divided by 58.44, and I get, on my calculator, 1.0267. That should be enough significant figures. And then 120 times 1 exponent 3 negative, and I get 0.12. So this first number is in moles. The next number is in liters. And so we can throw this now into the molarity formula. So I'll write this down here. Molarity is equal to moles divided by liters. And so it's going to be 1.0267 moles divided by 1.12 liters. And let's see what we get. Okay, and the number I get on my calculator, I'll put it up here, is 8.5558 and so on. Now, what you have to do is convert this into the correct number of significant figures. And what I'm kind of hoping you'll notice is that we're kind of limited here to 2 significant figures because 120 milliliters, the first digits are significant, but we should assume the 0 is not. So we're really at 2 significant figures. So the answer for this problem should be 8.6 molar. But again, one other way you can write it is 8.6 mole per liter. And I should be careful and write MOL. Okay, let's move on. Okay, the next problem is kind of fun. You're going to figure out the molar concentration of sugar in a Coca-Cola. Okay, so what is the molarity of sucrose? In a 12-ounce soda, which has a volume of 354 milliliters, that contains 40 grams of sucrose. So let's figure out the molarity of that Coca-Cola. So we have molarity we're trying to figure out, and we have moles solute, and we have liters solution. Okay. So we have 40.0 grams of sucrose times 1 mole sucrose over 342 grams, because we've got to get this into moles. I'll just work that out now really fast. 40 divided by 342, and we get 0.11695. Okay, liter solution looks like we have 354 milliliters. We're going to have to get that into liters. Kind of know that will be 0.354 liters. Okay, then remember molarity is equal to moles divided by liters, and so it's going to be 0.116959 divided by 0.354. Okay, and I get a number in my calculator, but let me just confirm. It looks like what we want is an answer in 3 significant figures. So the concentration of sucrose in a Coca-Cola is 0.330 molar. So that is pretty concentrated. So to give you an idea of how concentrated that is, keep in mind that salt water in the ocean, it has a molarity of sodium chloride of 0.5 molar. So this is not 0.5 molar, but it's pretty high, 0.33 molar. So it's a pretty concentrated solution of sugar in water for Coca-Cola. Okay, let's move on to the next problem. How many milliliters of solution would contain 25 moles for a 6 molar solution? So this is a bit of a different problem in the sense that we are now given the molarity. So note, it's 6 molar. When you see molar, then you're given molarity. That's not moles, that's molar. So we already know we're at 6.00 molar. How many milliliters? It looks like we're going to try to find volume. So that is our unknown. And then let's see, how many kilograms of sugar or excuse me, my mistake. Oh, okay, nope, I'm good. 25 moles. Okay, moles of solute. Little brain fart there. Okay, moles of solute is going to be 25.00 moles. Okay, so we're trying to find liters of solution. So let's see how we might go about doing that. So molarity is equal to moles of the solute over liters of solution. So what you need to do is you need to solve this problem for liters. And so what you have right now is you have liters on one side of the equation in the denominator. Now you might know that what you can do is multiply both sides by L, but another way you can think about this is if you move the liters to the other side of the equal sign, you switch the position from the denominator to the numerator. That's the same thing as multiplying both sides by L. So you can also say liters times molarity is equal to moles. Okay, but we need liters by itself. So we can move molars, excuse me, we can move molar to the other side of the equal sign by putting it in the denominator. So liters is equal to moles divided by molarity, or molar will be fine. Okay, so I think at this point we can plug in numbers and get an answer for liters, then we'll convert this into milliliters. And so let's see. Liters is going to be equal to moles, which is 25.00 moles over molarity. Now again, we have 6.00 molar. It's the same as 6.00 mole per liter. So let me write in those units into this problem. So 6.00 moles per liter. So let's talk about what the units end up being. We have moles in the numerator here of this fraction, moles in the denominator, so the moles cancel. We have liters in the denominator of a fraction that's in the denominator of another fraction. If that is the case, then liters goes into the numerator. So the answer will be in liters. So let's just see what we get in liters. So it's going to be 25 divided by 6, and we get 4.1666 and so on liters. And then I think the problem is asking for milliliters. Okay, so you have to get this into milliliters. So what I'll have to do is do this. The liters cancel. And so as I recall, you should get the following number in your calculator. But what we want to do is convert this to correct number of significant figures. It looks like in this problem we have to get things in 4 significant figures. So it's going to be 4167 milliliters is your answer, or 4.167 times 10 to the 3 milliliters should be the answer. Okay, let's move on. How many kilograms of sugar are needed, and there's the molar mass for sugar, to prepare 1.5 molar solution in 2.7 liters of water? So let's set this up. Molarity, moles of solute, liters solution. Okay, so what do we have? Looks like we know the molarity for this problem, so it's 1.5 molar, which is 1.5 mole per liter. And it looks like we know the volume of the solution. The volume of the solution is 2.7 liters. But what we're trying to do is find the mass in kilograms of sugar needed to make this solution of 2.7 liters at 1.5 molar. So we need to figure out first the moles of solute, and then somehow we need to get that into kilograms. So let's go ahead and just plug in numbers and then solve for moles. So let's set up the equation. So molarity is equal to moles over liter. And so let's just solve this for moles. So we can multiply both sides by liters, or we can move the L to the other side of the equation. It was in the denominator, it'll go in the numerator. So another way you can do, or that's another way you can do it. So moles is equal to molarity times liters. So let's go ahead and do that. So the molarity is 1.5 molar, so I'm going to write 1.5 mole per liter. And then we have 2.7 liters. And you can see that the liters will cancel, leaving an answer in moles. So let me go ahead and do that math. So it's going to be 1.5 times 2.7. Let's see where we're at. Okay, so what I got is 4.05 moles. Now, it looks like what we're dealing with is sugar. So that is sucrose. I'm going to write sucrose here for sugar, which is fine. Now, we have to get this in kilograms. So I suggest you convert first moles to grams and then grams to kilograms. So let me go ahead and quickly set this up. So it's times 342 grams in 1 mole. So the moles would cancel out, leaving an answer in grams, and then we have to convert grams to kilograms. So it's going to be times 1 kilogram over 1,000 grams. Grams cancel out, leaving an answer in kilograms. So it's going to be 4.05 times 342 divided by 1,000. So the number I get in my calculator is 1.3851 kilograms. And so it looks like we're going to be limited to 2 significant figures in this problem. So the answer should be 1.4 kilograms of sucrose. Okay, let's move on. How many moles, molecules, and grams of nitrate ions are there in 300 milliliters of a 0.5 molar solution of barium nitrate? Yikes. Okay, so let's see how we're going to set this up. So molarity here, moles of solute here, and liters of solution here. So it looks like one of the things we're going to probably have to find is the moles solute, but that won't be enough. We'll have to find out the number of molecules of nitrate in this case. It's not barium nitrate of nitrate, so that's something we have to keep in mind. And we also have to find the grams of nitrate. So that's going to be a little bit of a complicated problem. So we have 300 milliliters, so liters solution. So we're going to have to take 300 milliliters, and let's go ahead and right now and convert this into liters. So this is what I would do, times 1 times 10 to the negative 3 liters over 1 milliliter. And I think if you work this out, you will find that we're working with 0.3 liters of solution. And so we are given information here of the concentration is 0.500 molar. So 0.500 molar, which is equal to 0.500 mole per liter. Okay, so let's look at the formula for molarity. Molarity is equal to moles divided by liters. And so again, we're going to solve this for moles. And so we already know that moles is equal to molarity times liters. And so let's go ahead and get that far. So molarity is 0.500 moles per liter times 0.3 liters is the volume. And let's see, 0.5. Okay, so and I get 0.15, and the units should be moles. Okay, so we're now at this point where we have 0.15 moles. Now, here's the problem. What we were doing in the original problem was dissolving the compound barium nitrate. So this would be the moles of barium nitrate. So I'm going to write barium nitrate here. But here's the problem. We're not looking for the moles of barium nitrate. In this problem, they're asking for the moles of nitrate ions. So you have to convert the moles of barium nitrate into nitrate ions. So that actually isn't too difficult, because as you learned maybe a lesson or two ago, look, if we have 1 molecule of barium nitrate, how many nitrate ions do we have? So nitrate is NO3 minus, right? We have 2 nitrate ions for every 1 molecule of barium nitrate, which means is you'll have 2 moles of nitrate ions for every 1 mole barium nitrate. So we have 0.15 moles of barium nitrate. So we can convert that into an equivalent amount of nitrate ions like this. So it's times 2 mole of nitrate, get rid of the E, over 1 mole of barium nitrate. So let's see what that is. Oop, yep, got it. Okay, so let's see where we're at. Let me clear off some space. Okay, so it looks like right now we can do this math and get the answer as 0.30 moles of nitrate. Okay, but we need to get more information. Okay, so one piece of other additional information that we need to get is the molecules of nitrate ions. So if we know we have 0.30 moles of nitrate, what we can do is multiply this by Avogadro's number. And that should be the molecules of nitrate. So let me go ahead and do that. And I get 1 point, I'm trying to figure out the correct number of significant figures. Let's assume in the problem the 300 milliliters, let's assume that those zeros are significant. I should have had a decimal after those zeros. So we should get an answer in 3 significant figures. And again, let's assume that all those zeros in 300 are significant. Should throw in a decimal there. So this should be 1.81 times 10 to 23 molecules of nitrate. Okay, and then the final thing you need to do is let's figure out what the mass of the nitrate we have is. And that's pretty simple. So it's 0.300 moles of NO3. I'm just adding an extra 0 here, so we should be at 3 significant figures in the problem. And it's a calculator number. Times the molar mass of nitrate, which is 62.00 grams per mole. So the moles nitrate cancel, leaving us an answer in grams of nitrate. So it's going to be 0.3 times 62. So I get 18.6 grams of nitrate. Should be the answer. Okay. Thank you for listening. We'll see you next time.